Hello students, in this set of videos we're looking at Maclaurin series and Taylor series, and these stem from a power series which we defined last class. So remember that with a power series we can have an interval of convergence. It's either a single value, it's a range of values, or it doesn't converge at all. If I do have a convergent power series, then I can express it this way. Within my domain I, this function can be differentiated or integrated. And the fact that this is true helps me to determine what my coefficients are. So remember, if x was equal to a, then I know that this converged because it turns into just the value c sub 0. So let's write that down. At x equals a, f of a is just my c sub 0 term. Well, if I take the derivatives, then I get this function. So my constant becomes 0. When I take the derivative, the first term, I would have a 1 here, so take the derivative, 1 comes in front, times c sub 1, x minus a to the 0, etc. So here's my derivative. So then the first derivative at x equals a, all of this will go away, and I'll have c sub 1. So at x equals a, f of a is c naught, f prime of a is c1. If I take the second derivative, I'm going to get 2c2. This will go away. This goes away. 6c3 times x minus a, 12c4 times x minus a squared. So the second derivative at a, everything else is going to go away, but I'll have just this term left. So if I have my second derivative, then I'm going to get the second derivative at x equals a is equal to 2c2. Well, that implies that half of the second derivative is equal to the second constant. If I take the third derivative, well, at that point, let me just write down my second derivative is going to be 2c2, that goes away, plus 6c3, x minus a, plus 12c4, x minus a squared, etc. So again, at x equals a, second derivative, 2c2, so c2 is second derivative at a divided by 2. Well, c3, when I take the third derivative, this goes away, I'll get this. So my third constant is going to be the third derivative at a divided by 6, but of course that 6 came because it was 3 times 2. So I'm going to say it's 3 factorial. We can continue on in this way, and that leads us down further in the notes where we figure out about how to solve for these constants. So we can use the derivative to solve for the constants. That's what this is talking about here. So here I am finding my first derivative at a gives me the first constant. Second derivative at a gives me the second constant if I divide by 2, etc., etc. So I can solve for the constants by saying the nth derivative at a, so this is my derivative, over n factorial. So our power series can be expanded that way, and this lets us define a Taylor expansion. So we say that the Taylor expansion around a, so I'm thinking of f of x around a, it can be approximated from my polynomial to say that I can end up solving for these constants. So when I expand my power series, I would get c0 plus c1 x minus a plus c2 x minus a squared, etc. But I've just said that C0 is f of a. C1 was first derivative of a, divide by 1 factorial. C2 was second derivative at a, divide by 2 factorial, times x minus a squared. That continues on. This is my Taylor expansion. So if I continue to infinity, I have f of x. But if I just go to a certain number of terms, then I have the nth Taylor expansion. So the Taylor expansion is when I look for some value a. If I make that value of a 0, I call that the Maclaurin series. So both of these are approximations of our function, and they're really just the power series expansions, but plugging in values for the constant, which come from the derivatives. We're going to look at some examples of this coming up, but read through these other notes and make yourself some notes about them.